Another kind of bearing that makes mechanical contact is a flexural bearing, because it's always in contact. And a flexural bearing you'll find all over the place, from the ubiquitous shampoo bottle top to, for example, drink containers. Here's a drink container which has a top that's on this interesting rotary bearing here. And when you look at the function of this, implies, oh, to open it, I push up. And I can, and it comes up. If I push at the wrong angle, though, see the way I'm pushing? If I push in, it won't open. If I push up, it won't open. I have to push. I gotta. That's pretty hard to open. But why does it just open that way? It seems like I'm pushing there, and it's not really opening. But then it did, versus now I don't push at all, and it opens right up. Versus sometimes it won't open at all. What's the magic that's happening? Well, if you look at it closely here, watch what happens when I squeeze. Maybe it's very subtle, but maybe look here even a little closer. It's round, and this lip is catching on this tang sticking out. And when I push here, the round turns oval, and the axis of that ellipse is of a larger diameter than the initial circle. So it snaps shut. It'll hold its own weight sometimes. See, when I'm holding its weight, I'm squeezing in, which is making it release. If I squeeze, it opens right up, and here it's not. So a flexural bearing can give you amazing, wonderful, interesting properties, but because the motions are often small, you have to be very careful of unintended motions and consequences. Those unintended little motions are called parasitic error motions, or parasitic motions. And they actually happen with many different types of bearings. It's all very predictable using mechanics of solids, and you can use your understanding of mechanics of solids and bending of beams to create all kinds of flexural bearings, from rotary hinges to flexural linkages, or I like to call them flinkages because it's kind of a cool word, but most people call them flexural hinges or just flexural linkages. And remember what we just said about parasitic motions, and look at this picture of a bending beam. So when you have a beam, just a simple cantilever, and you push down on it, there is a slight shortening of the beam. Very predictable. You can read the formulas in the text and even their derivation. And that bending of the beam, if the large bending is delta, this little delta, or the parasitic motion, because that's usually unwanted, is typically less than an order of magnitude smaller than the large deflection, but it's there. And for some types of structures, that can be unacceptable. Fortunately, for that problem, if we invert it literally, you can have a solution. So watch how we can apply the power of reciprocity, essentially, to get rid of that problem by imagining this as a center line and mirroring. Let me use a different color. If we mirror this structure over here, then when this one bends, we can ask ourselves, how can these two cancel? And indeed, if you look at this type of structure here, where we have these flexural linkages, if this structure here is anchored to ground, and when this platform moves, this beam bends and wants to get shorter, dragging this structure in. But when this beam bends to ground, it also wants to get shorter. So this side moves inward. The floating platform doesn't move over, because if you look, play the movie in your head of these two beams here. They were straight like this, and then now they're like that. This end here didn't move at all. It's just their end was allowed to move in. That's this floating platform. Okay? Here is our center line, and we do the exact same structure on the other side. Sometimes this is referred to as a folded flexure. This thinking about how bearings deform in the way you want them to move, and always being cognizant of what other little things are happening as things are moving, these parasitic motions, and being able to predict them, and being aware of them, and then being able to predict them and determine if they're a problem for the functioning of your machine or not, is critical for the design of robust machinery. If they are a problem of your machine, you ask yourself the question, well, how can I make them go away by either just making it much stronger, stiffer, but that doesn't always get rid of the parasitic motion in the case. For example, here, it's just a function of the geometry. Or how can I use reciprocity or make a structure a mirror image of itself and use one parasitic motion to cancel another? That's a very, very powerful part of design, is that use of reciprocity and canceling error motions. Another example of canceling motions that you don't want is this device here, invented by a friend of mine, Dr. William Plummer at Polaroid. And this device here was designed such that you could put a lens object in here that they wanted to do calibration of, where they wanted to get pure tilt of a lens. This is, I believe, for the SX70 camera long ago, one of the most sophisticated cameras ever actually designed. They need to get pure tilt with no translation. You could do that with a very, very expensive stage system, or Bill created this flexural bearing system here that includes a transmission. And let's look and see how that one works. And demonstrating the principle of reciprocity and how you work with the mechanics of structures. You start with a cantilever beam, length L, put a force on the end of it. The beam has a modulus of elasticity E, moment inertia I. Okay? That beam, when it bends down, it'll have a slope at the base, theta equal, well, we use alpha, excuse me. Alpha equals FL squared over 2EI. The deflection, delta, is going to equal FL cubed over 3EI. So if you were to mount the lens element you're trying to create with pure rotation at the tip of the beam, you would get, for example, the slope you want, but you'd also get this deflection, which from the function required would be a parasitic motion. On the other hand, if, as the figure shows here, you have this arm reaching back, just attached to the tip of this beam. In other words, here I'll draw this in 3 dimensions. Like that. Okay, so here's our lens element back here. Remember the principle of the Abbe error, Abbe offset. There's no forces on this middle beam. It is going to have the same slope as the side beams do, which have the forces applied to them, which means that there is some point where I can use this angle times some length to cancel, for this application, what is the parasitic error motion. And if I look at the ratio of these two, it tells me that if I take alpha times L2 over 3, I will get delta, right? Because 2L over 3 times FL squared over 2EI is going to equal FL cubed over 3EI. And I can exactly cancel this parasitic motion. Now what about these, what are these purple dudes and this other beam behind it? What do they do? Well, what Bill wanted, he not only wanted to be able to adjust the pitch of the lens, he wanted to also adjust the roll of the lens. And that's what made the calibration stage he needed so complicated with respect to stacking together traditional cradles to form a gimbal type structure. You can do it, but for just the small motions he needed, it would be rather expensive, and they needed a lot of these systems for production. By using two of the beams, watch what happens. If I take a beam and below another beam, and I'm going to purposely draw it thinner, and then I put like a set screw in here, which is threaded in the lower beam and just touches the upper beam. So now I've got these two beams. As I push on the screw to say, I start like this, and now I'm going to lengthen the screw. It's going to pry these two apart as I tighten the screw here, and it goes, yeah. And these beams will now spread apart. But notice this, if this beam is of thickness T, and this upper beam is of thickness big T, I have the force on from the screw is action and reaction, equal force on both beams. The deflection of the upper beam is going to equal what? Well, it's going to be the force of the screw, force from the screw, times, and this is L, L cubed over 3E, and now the width of the beam, and with B, B T cubed over 12. Is that the deflection of the upper beam? And then this is the upper beam. The deflection of the lower beam equals F from the screw L cubed. Let's assume it's all the same material. 3E, and the beams are the same width, little t cubed over 12. But when the lower beam deflects, it carries the screw with it. So what does that tell you about what happens with the upper beam with respect to the lower beam? Well, when you do apply the screw never really applies a force so much as when I'm adjusting this thing, what I'm really doing is I'm applying a displacement to the screw. Okay? So, for example, one turn of the screw, if the screw has a pitch of 1 millimeter, means the screw will lengthen up by 1 millimeter. In other words, that the screw motion, let's call it delta of the screw, is going to equal delta of the upper beam plus delta of the lower beam. The lower beam is going to deflect down, the upper beam is going to deflect up. The sum of those two deflections are the amount that I move the screw. So hence, the transmission ratio that I'm going to get from this system is going to be the ratio of these two equations here. Okay? So if I, for example, because it goes by the thickness cubed, have this upper beam being 2 millimeters thick and the lower beam being 1 millimeter thick, 2 to 1, so 2 cubed, 8. So if I have 8 to 1 transmission ratio simply by using these two flexural beams. So I can take that screw, which would normally have a pitch of 1 millimeter, and it has, with respect to the upper beam, has a virtual pitch of 1/8 of that. So flexural bearings are not only so interesting that they can provide this motion that has no backlash, that has no wear, requires no lubrication, Their only limitation is the range of motion is kind of limited, but I can also use them not just as a simple bearing, but as part of a transmission system. Very, very powerful tool. The other thing to note about flexural bearings with respect to consumer products that you may design, and even industrial products, for example, here is a structure that's all injection molded. It clamps over and then snaps closed with a snap connect, and this is for holding cable bundles. So this structure, you would, with these adhesive elements, adhere down on your machine, lay your cable bundles in it, and then just snap, 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 snap. So the bearing has a large range of motion, but only applied for just a couple cycles. Lids for drink containers, rotary flexural bearings, often called C-flex couplings. There's a fantastic array of flexural elements. Here's another flexural bearing which is used in a transmission ratio. My friend Nelson Hathaway invented this design. When I move this structure up and down, so there'd be a micrometer here where I could control this motion to the thousandth of an inch level, it's creating a strain field over here that is causing this surface here on this little 4-bar flexural linkage to move that way 1/1000th of this motion. So in other words, if I move this here 1 millimeter, this stage here has gone 1/1,000,000th of a meter in motion. That's fantastic. Now you can't make this stage move 10 millimeters by this method, but for very, very, very fine control, for example, in some special types of microscopes or cell manipulation systems, you can use this kind of effect. Flexural bearings also have a very special place with respect to rolling motion, and indeed have been used for designing prosthetic replacement joints. Where they're used is if I have one surface that wants to roll over another, but you don't want the surfaces to come apart, you want to guide their rolling through a motion, even, for example, a cam-shaped motion, not necessarily even round on round, but this could be an irregular cam with another mating surface on it. These bands, see this wide band here, it comes through, goes between these two bands and wraps around on the other side of this structure. These two bands come in, wrap around, and then attach on this side of this structure. This forms a rolling flexural contact bearing. This type of structure here, designed by my friend Mike Everman, this is a cutaway view for a stage that moves up and down, small amount of motion, but has extremely high pitch and roll, and even actually yaw stiffness. And it uses this same effect through, notice these copper-colored parts here. This is how, and here's this green one bearing coming around, and the blue guy coming around. And you end up with a structure with the bands on it that allows one to move with respect to the other, and where the purpose of this intermediary roller with the bands is to cause, when this structure moves up and down with this rolling element band, it can't do that because the geometric constraint is that both sides of these rollers have to move up and down at the same velocity. And the same thing with the two on this side. For tools, laparoscopic tools, for the joints at the tip, or emulation of finger joints, these rolling flexural contact bearings can be very, very, very powerful. In a sense, they're emulating what happens in your joints. And if you were to go and you were to look at the structure in your knee, the way your MCL and your ACL goes and the ligaments wrap through the knee, you'd see the same kind of flexural type bearing for the ligaments in there, although you have sliding contact in the knee. But the same idea behind ligaments that hold your joints together. That's the motivation. Speaking of knees, what type of lubrication do you have in your joints? We just said that, for example, in your knee joint, you've got sliding contact. And in your shoulder joint, for example, any of your human joints, you've got sliding motion. The speed is very low, so that sliding motion tends to be what's called a boundary layer. You never build up a hydrodynamic wedge, which is what happens when you start sliding on the beach. When you take your boogie board out and you go running, and you throw it down on this where the surf has just been on the sand. You jump on the board and you slide along. That's hydrodynamic lubrication. What happens in hydrodynamic lubrication is, for example, you have a bore and a shaft in the bore, and as the shaft is spinning, due to the viscosity of the fluid, it's going to drag fluid in and form what's called the hydrodynamic wedge. And that fluid being dragged in creates a pressure profile. This is shown by this blue shape here that will now act to support a load. As the load is applied when the shaft is spinning, the applied load causes the gap to get smaller, which causes, as the fluid is being dragged in, the pressure to increase, which then reacts against the load. So it's like a system of self-help. There is a relationship where the deflection of the shaft is related to the force applied and the speed of the shaft. The mechanics of this were first described by Osborne Reynolds back in late 1800s, early 1900s. He did the engineering science behind predicting this type of fluid mechanics. And then Albert Kingsbury lived a little bit later, late 1800s to the mid-1900s. Very famous person, for he took the idea of hydrodynamic bearings and invented what was called the Kingsbury thrust bearing, or the tilting pad thrust bearing. And many of his bearings built in the early 1900s are still in use. Where and how? What these tilting pad thrust bearings do, and tilting pad bearings for radial motion too, if you had a big heavy object that you had to support, let's say it was the turbine impeller for a giant hydro turbine at Niagara Falls for making power. So these are supposed to be turbine vanes, the water coming in and causing this to spin. How do I support this turbine disc? There's a huge thrust load from the weight of the structure, and in some turbines, axial flow turbines, you would have huge axial loads. Well, to make two plates perfectly flat that'll fit together and not have a high point somewhere such that you can have a hydrodynamic bearing is very difficult. It's also very difficult to imagine that if I want to resist a very high thrust load, how do I do that between this surface and this surface when I'm pushing down and spinning? Where does the hydrodynamic wedge build up, like we showed in this picture? Well, what Mr. Kingsbury did is he put a series of pads such that each pad was supported on a little rocker. So if you imagine you had this repeating pattern. If this tilts a little bit as the upper surface is moving, because you have a little bit of an eccentricity here, if this upper surface is moving and I have a little bit of tilt, I'll build up this hydrodynamic wedge and pressure profile over this tilting pad. And when I have a whole bunch of these tilting pads, it's now very easy to get them all. You never have to worry about them being aligned in tilt because they will self-adjust. They just have to have a common plane on their entire top surface when there is just a static load from the static load and no lubrication. Put the turbine impeller down here, push, and it should touch all of them. And remember we talked about earlier about rubbing a bearing, so that's how you could tell that they're all at the same height, by rubbing a bearing and scraping them as appropriate. So this brilliant invention, motivated by perhaps practical thinking, by understanding the engineering science behind the fluid flow for hydrodynamic bearings, really enabled modern society to happen, because for very large machines to this day, you will often use hydrodynamic bearings simply because they are so robust and so inexpensive. And they can last for a century. So where else do you find these bearings a lot? Hydrodynamic bearings are at the root of all internal combustion engines in cars. Those are the bearings that are used to support the crankshaft, for example, the main journals in the crankshaft or the camshaft. There are applications for rolling element ball bearings in cars, for the axles, for places where you have very high speed with a lot of start and stop. Because remember, when a hydrodynamic bearing operates, the shaft is spinning. If you stop, it touches down, and then it takes a little bit of speed before it lifts off again. So the application for hydrodynamic bearings is basically you're running continuous motion all the time. Okay? If you have start, stop, rolling element bearing is going to be a better selection. Well, we just said that hydrodynamic bearings work very well because when you have a small deflection in the shaft, that's what enables the hydrodynamic wedge to build up in the first place so it can support a load. But what if I need a high degree of accuracy where I know that I must have the position of the shaft in a spindle to always be known and to be as stiff as possible. So I don't want to have to get it up to speed in order to establish the accurate motion of the spindle. Well, a hydrostatic bearing has an external pump that pumps in pressure into the bearing to lift and support the shaft, or a carriage if it's for linear motion. And remember, hydrodynamic bearings can also work for linear motion machines also. Any of the bearings we're talking about, there's always going to be a linear and a rotary motion analog. So hydrostatic bearings rely on external pressure and a very specific way of regulating the pressure. And let me expand on this picture here, this circuit diagram, to show what happens. Let's say I have this block that I want to float in a structure. So an end view of this would be something like this. So for example, this is a bearing rail, long, very precise piece of metal, ceramic, structural material, and a machine tool. This guy here. And then this around it would be my carriage that moves in and out of the page. And indeed, you would often see a machine that, with a whole machine, looks something like this. Oh. These are the keeper rails. And then I'm either going to put my hydrostatic bearing elements here. And watch the way I'm doing them. They're always working in opposite, well, not always, usually working in opposite pairs. And there. Or I would have put one in the middle And then these would be my hydrostatic bearings. Let's see the way these things work. The hydrostatic bearing assumes you have, let me use a different color here. That you have a pocket. And I have to get fluid flow into the pocket. And so this is not floating in air. Let me just make this like this is anchored to ground, okay? So I'm going to bring in fluid flow into that pocket. And if all I do is provide pressure from a pump, I'll have pressure applied over the area in the pocket to the top and the bottom, and force equals pressure times area. So I have the same force on the top and bottom, and this thing has no stiffness, and then just clunk. It'll go either way. And you say, yeah, but if you push down, this will form a seal in here, and it's got to pick it up. But if it's the same pressure either side, you say, well, it's not going to be the same pressure, because if you push this down, there's no gap here, there's a big gap here, and it's going to have to leak and have a lower pressure. And now, by that reasoning, you're starting to realize, aha, I actually don't want to have pure pressure from the pump applied to both of these pockets. I want to have the pressure that goes into each pocket actually go in through a resistance. This is called the compensation unit, or how you compensate the bearing. This flow out we'll call the resistance of the pad, or the pocket. We'll use pocket. We just call it RP, RC, and then pressure of the source. And this one will be, let's say, for the lower part. And then here, the resistance pressure for the upper part. And this is the resistance, this compensator for the upper part. A circuit analogy is the following. Here's the resistance of the compensator for the upper part. Here is the resistance from the pocket from the upper part. Its resistance is variable based on how this carriage moves up and down. So it's a variable resistor. And then it flows to ground. Similarly, you have the compensator of the lower part, resistance of the pocket lower, and this is also variable. And then over here we have the supply pressure. These two compensation resistances are equal. One goes higher, one goes lower, or one goes higher and one goes lower as this moves up and down. The pressure inside the pocket, pressure pocket lower, pressure pocket upper, depends upon the ratio of the resistances. You can read the detailed math in the text. Suffice to say, it works great. But, like with many things, manufacturing is the absolute key to detail, because these resistances are a function of the bearing gap to the third power. In other words, this bearing gap in here, H, the resistance goes like 1 over H cubed. And here's the viscosity of the fluid. Okay, so as the gap gets smaller, the resistance goes up very fast. And it turns out that to make this a stable, well-behaved system, that when it's normally sitting with this gap equal to that gap, no loads, you want the compensating resistances to be equal and also equal to that bearing gap. But if you make for the compensation resistance just a simple capillary, a small thin tube, the resistance of the capillary tube goes like viscosity of fluid over the diameter of the capillary to the fourth power. So the smallest variation in the diameter of that capillary can cause a huge swing in the resistance. So these types of bearings can be very difficult to balance. It requires a lot of skill in the design and the selection of the tolerances. Fortunately, whenever you run into a problem like, God, that's really hard to do, well, all right, we'll use a lot of skill. Oh, I wonder if there's a better way. So there are designs that are called self-compensating designs, where the structure of this compensation unit actually gets its resistance from the bearing gap on the opposite side. And there's a number of different ways of doing this. They all rely on the principle of self-help to allow them to self-tune to give you the optimal compensation resistance. So you can read about those. Now, the other type of hydrostatic bearing or aerostatic bearing uses air instead of a liquid. For a liquid, you may use oil, and oil is very nice. The resistance is easy to achieve that you need in your system because of the high viscosity of oil. Oil can be environmental difficulty sometimes, so you say, well, we use water, and we've designed and built a bunch of water machines, very high performance. The water self-cleans the surfaces, works very well. But you don't always want to have a lot of water blowing out. So what else could you use? Air. These, see, here's a small modular air bearing. A guy named Drew Devitt at a company called New Way Precision makes these. And what New Way does, he takes porous graphite, bonds it into a metal housing, then, for example, a spherical element allows it to tilt self-aligned but very stiff rigidly in the axial direction. Put the air in, and then with air in, it'll float on a thin layer of air. Think air hockey table. This being a modular element, as we show here, for example, you can take these and instead of applying air pressure, apply suction and stick them to your structure, bring your carriage around them, position it with respect to the structure, and then either they're mounted and adjusted with a screw thread with these tilting pads by virtue of a screw thread and then a ball end on that screw. Or for very, very precise systems, you can then pump epoxy behind them and fix them in place permanently until you break the epoxy without having to precision machine your carriage. So some very interesting novel ways have been discovered for making very, very high precision machines using very, very simple structural elements, air bearings. You can also use this method with hydrostatic bearings. That's actually how we do these big ceramic water bearing grinders. And achieve very, very high load capacity, high stiffness, and a virtual immunity to dirt. It's never not a downside to things. You have to have a pump, and you have to keep your fluids managed in terms of clean. But the performance benefits for many types of precision machines are clearly marked. Now let's go even more interesting. Magnetic bearings. We've all played with magnets before, where if you put a north pole to a south pole, they stick. But if you go to put a north pole to a north pole, they repel each other. Now, to have stability, you need to have, in a magnetic bearing, servo control or active control, where you're sensing the gap and using that gap back into the control of an electromagnet to create a stable floating of the bearing so it doesn't stick one way or another or run out to the side. But the principle of magnetic bearings, like hydrostatic bearings, mean that you can have no contact, physical mechanical contact between structures. And when you have no physical mechanical contact, just a fluid layer, either from the fluid being hydrostatic or hydrodynamic, or the absence of all fluid and still having a gap, which is what you could do with magnetic bearings. Now you don't have to rely on a pump. You have a servo system, but you don't have to keep your fluids clean. And because if you run it in a vacuum or with fairly large gaps that you could never run an air bearing at, you could run at incredibly high speeds without generating shear power or the friction of shearing a fluid in a thin, small gap. These bearings are used quite extensively, actually, to support shafts of machines that have to run under very high loads continually. For example, compressor shafts for natural gas pipelines. They're often run using magnetic bearings. For super precision motion, linear and rotary, where else would you use these kind of bearings? Where else do I need the highest of high precision where the smallest little error, even on the nanometer level, starts to cause me problems? Well, that happens in some of the most sophisticated machines on the planet, known as wafer steppers, where wafer steppers are those devices used to transport silicon wafers under lenses so that you could print the pattern of the integrated circuit onto the silicon. The stages, those are the devices that carry the silicon wafers at very high speed, very high precision around under the lens stack so that the individual silicon die, can have their circuits printed on them. Those stages are typically supported by magnetic bearings because they can not only be very fast, you can actually measure the position of the stage as it's moving using laser interferometers, feed that signal back into the machine controller that senses when the stage is moving not the way it should be, and magnetic bearings then servo, that means active control, the motion of the stage to eliminate parasitic error motions and get the highest of high precision. That's where magnetic bearings really in the end are the ultra super primo of bearings. Very sophisticated analytical tools are needed to design them, but once designed, fairly straightforward to build over and over again. Everything has a downside. I have external controller, cost, and we said earlier that the nice thing is that the gap can be large, so I'm not shearing a fluid and generating heat the way I'm in a hydrostatic or hydrodynamic or even a rolling element bearing indeed. But the coils, the electromagnetic coils, actually can generate quite a lot of heat in a magnetic bearing. So heat will have to be managed in those bearings also. Again, you can do anything with good engineering, which really boils down to a good accounting of keeping track of all the energy sources in your machine, how they cause the machine to deform, and thus create the parasitic error motions or undesirable motions that can affect the performance of the machine. That really is the name of the game of designing any type of machine.